We're talking about permutations and combinations in this section. So a permutation is an ordering of distinct objects. If we select R different objects from a set of N objects and arrange them in order, this is called a permutation of N objects taken R at a time. So let's see what this could look like in notation. So the number of N objects taken R at a time is denoted by P parenthesis N comma R. So this tells us there will be this number of objects and we're going to take this many at a time. So the P can remind you of permutation because we'll also learn combinations with a C, and then the number of objects to choose from, and then the number of objects are chosen, or the R. So if we look at P5, 3, we look at the counting permutations, which are the ordered arrangements, formed by choosing 3 different objects from a set of 5 objects. So if we have 5, so I've got 5 pens here, or 4 pens and a pencil, 5 writing utensils. So I'm looking at how many different ways that I can choose 3 out of the 5. So I could choose those 3, I can choose these 3, I can choose the 3 in the middle, I can choose these 3. So there's lots of ways you can choose them. So you're looking at 5 objects, choosing 3 at a time. So let's go look at, remember, we're going to use the fundamental counting principle in this. So let's look at example 1. So we're looking at counting permutations. So for part A, we want to know how many permutations are there of the letters A, B, C, and D. So this is without replacement, so we can't repeat them. We're only looking at the permutations that happen if we don't replace them. One at a time, we won't replace, okay? Or not really one at a time, but we're not going to repeat, so they won't repeat. So we're going to take those 4 letters, and how many ways can we do this? So if we draw the first letter, we start out with 4 choices, A, B, C, and D. So we have 4 choices for that one. If I draw the second letter, I had 4, but I drew 1 because I can't repeat them. How many choices are there? Well, there are 3 choices. All right, now if I draw the third letter, the third one, I've already drawn 2, so there are 2 choices left. And then as we draw the fourth, I've already drawn 3 of them, so there's only 1 choice left. So let's replay what's going on here. This could be any letter. This one can't repeat. So once I draw that letter, I can't repeat it, so it's down by 1. This one can't repeat as well, and I've already lost 2 of them, and I can't repeat the 4th letter either. So if I multiply, 4 times 3 is 12, times 2 is 24, times 1 stays 24. So if we look at this in permutation notation, this would be P 4, 4. So the permutations of 4 objects taken 4 at a time, so they're going to grab 4 objects each time, but they're going to be in a maybe a different order, and that's going to be 24. That's what's happening with permutations. All right, let's look at a second part. So how many permutations are there of the letters A through G. So A, B, C, D, E, F, and G, if we take 3 at a time. So how many do we have? We have 1, 2, 3, 4, 5, 6, 7 letters. So for the first, we would have a total of 7 because it could be any letter. For the second, we would have 6 because we can't repeat. So we have to take away that one. And then for the third, we are going to have 5 because again we can't repeat. And if we multiply 7 times 6 times 5, we end up with 210. So if we look at the permutations of 7 objects to choose from, taking 3 objects at a time, we're going to get 210. So this is to get you to understand what's happening with the permutations. Now we're going to go learn about factorial notation. So factorial notation, if n is counting number, the symbol n factorial, which is an n with an exclamation point, called that n factorial, stands for the product of n times n minus 1 times n minus 2 times n minus 3, all the way down to 2 times 1. We define 0 factorial to be equal to 1. So permutation formula, so we were looking at before what the permutation is happening, but the formula, to make it a little bit easier, we're going to take that same notation we were looking at, and whatever the number of objects are, we're going to put that on top at factorial, and we're going to divide it by the number of objects minus how many we're taking at a time, factorial. So we're going to go look at our next example. We're going to look at example 2. So for our first one, we're going to do part A. We're just going to compute these. So if I give us 6 factorial, I want you to understand what that means. So 6 factorial is 6 times all the numbers below it. That's what that whole notation here meant. It's going to be all the numbers all the way down to 1. So if we have, this would be equal to 6, the number below it, so n minus 1, would be times 5, times 4, times 3, times 2, times 1. Now we'll start writing those with dots. So 6 times 5 times 4 times 3 times 2 times 1. It makes it look a little less cluttered. And if I multiply that out, we're going to get 720. And you could use your calculator to multiply all those, or you can do it in your head if you want to. Okay, let's look at part B. So for part B, we have 8 minus 3 factorial. So that means we have to change this. 8 minus 3 is 5 factorial. So this would be 5 times 4 times 3 times 2 times 1, which will get us 120. All right, let's go look at part C. If we have 9 factorial over 5 factorial, on the top we would have 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And on the bottom I have 5 times 4 times 3 times 2 times 1. Now if you notice, from 5 on down, they match. So these would all cancel with these. So we end up with 9 times 8 times 7 times 6, which will get us 3,024. Now, what we can do instead is we could realize that this is 5 factorial, because it's 5 all the way down to 1, as well as this is 5 factorial. So when we see 9 factorial, 5 factorial, what we can do is do 9 times 8 times 7 times 6 times 5 factorial over 5 factorial, because we know that these are going to be the same numbers and we can cancel those. So this ends up still being 9 times 8 times 7 times 6, which is 3,024. So we get the same answer. This is a little bit less work. All right, let's go look at another example. So if we look at part D, we're looking at 8 factorial over 5 factorial times 3 factorial. Well, on that top, we're going to stop at 5 factorial, just like we did with the 9. So we'll have 8 times 7 times 6 times 5 factorial divided by 5 factorial, because it's the bigger one, and then we have to do the 3 times 2 times 1. We still have to multiply by what's in this one. So the 5 factorials will cancel, and we'll be left with 8 times 7 times 6 over 3 times 2 times 1. Well, 8 times 7 times 6 will get us 336, and 3 times 2 times 1 is 6, and that will get us 56. So you're going to save some time and effort, especially if your numbers are bigger, if you can recognize those factorial parts there. All right, so let's again talk about our formula here. We've got this formula that we've discussed and what's going on with it. So we're going to go back and look at that, back to example 1B that we did earlier, when we were finding the number of permutations of the letters. So we're going to go back and look at this one. And we wanted to see how many permutations we got. But we're going to work it out, not this way, but we're going to look at it a little bit different. So this will be example, it's not really listed an example. We're just going to kind of go back and look at it. So we'll do example 1B again, is what we're going to call it. So we are looking at, we were doing a permutation. We had 7 objects, 3 at a time. So if we do the P at 7, 3, if we use that formula, remember it was P of n, r is equal to the n factorial over the n minus r factorial. So we've done some things that look like that. So understand that this is your n and that's your r. And if you need to, label them so you don't lose track. So when we look at this, our n factorial will be 7 factorial. And on the bottom, we'll have 7 minus 3 factorial. Well, that's going to be 7 factorial over 4 factorial, because 7 minus 3 will get us 4. So now we're going to have 7 times 6 times 5 times 4 factorial over 4 factorial, which means those will cancel. And we end up with 7 times 6 times 5, and when we multiply those out, we're going to get 210. And that is the same answer we got when we multiplied out the choices. So this is what we're now doing, but we're doing it with a formula. And in some ways it will be easier, especially if you're doing bigger amounts of numbers. All right, so let's go look at example 3. So we're going to count ways to fill a position at a community theater. The 12-person community theater group produces a yearly musical. Club members select one person from the group to direct the play, a second to supervise the music, a third to handle the publicity, tickets, and other administrative details. And how many ways can the group fill these positions? So we have 12 people that are in the group, and we want to choose 3 people out of the group. So this will be example 3. So we're looking at the permutation out of 12, we're going to choose 3. So using our formula again, remember this is our formula right here, we're going to do 12 factorial over 12 minus 3 factorial. So that'll be 12 factorial over 9 factorial, which is going to get us 12 times 11 times 10 times 9 factorial over 9 factorial. And then we don't have to always write it out as 12 times 11 times 10. When we multiply those, we're going to get 1,320. All right, so now let's change things up just a little bit. Let's go look at combinations. So let's change the conditions of example 3 slightly. Suppose that instead of selecting 3 people to carry out 3 different responsibilities, we choose a 3-person committee that will work jointly to see the job gets done. So in example 3, if A, B, and C were selected to be in charge of directing music and administration respectively, that would be different if B directed, C supervised the music, and A handled administrative details. With the new plan, it makes no difference whether we say A, B, C, or B, C, A. So we're saying that order doesn't matter anymore. So here would be the choices. We have directing, music, administration, and then we could switch these two, and then we could switch those, and then we could switch all of them around, and we could see going, and we can see that we're going to end up with several different ways that this is happening. So we can see by the table that all of the 6 different assignments under the old plan are equivalent to a single committee under the new plan. So what we're saying is that this applies to any 3 people in the theater group. So the answer of 320 is too large. So we must reduce it by a factor of 6 under the new plan. Remember that 6 is really 3 factorial. That's 3 times 2 times 1, which is going to be the number of ways we can arrange 3 people in order. And that's what we came up with those different ways we can order it. We have 1, 2, 3, 4, 5, 6. So the reason the number is smaller is now that we are concerned only with choosing a set of people to produce the play. The order of the people chosen is not important. We can generalize what we just saw. If we are choosing our objects from a set of n objects that are not interested in the order of objects, then to count the number of choices, we must divide P and R by R factorial. Now this is called combination. If we choose our objects from a set of n objects, we say we are forming a combination of n objects R at a time. So this is what our notation looks like. So it's basically taking what we know to be the permutation and we're going to divide by an R factorial. What you really need to understand is when you're doing a combination, you're also going to have, you could say like a combo at the bottom. So the P and R looked like this. This was the formula. Now we're going to divide by that R factorial. So on the permutation, we just had this. And now with the combination, we have the R factorial at the bottom. So think about combinations have a combo at the bottom. There's 2 parts. So we're going to divide by R factorial because we're not interested in the order. Order is not important. So here you have permutation, order matters. Combination, it does not. So using the combination formula, how many groups of 3 pictures from a set of 5 can you select to make a custom collage for your Facebook cover? So we're on example 4. And we're looking at part A, and we want to choose a combination. Out of 5 pictures, we want to choose 3. So with that formula, this will be 5 factorial over, we still have the 5 minus 3 factorial, like we would have done in the permutations, but now we also have a 3 factorial. So again, this is going to be C n comma r is equal to n factorial, still over the n minus r factorial, but you're going to add or multiply by an r factorial in the bottom. So the formulas look very similar. We're just doing this r part. All right, so on the top we have 5 factorial. We have 3 factorial on the bottom, and 5 minus 3 would be 2 factorial. So when we pull this apart, we're going to stop at 3 because it's the bigger number. So 5 times 4 times 3 factorial divided by 3 factorial times 2 times 1. 3 factorials will cancel. So on the top, we now have 5 times 4 divided by 2 times 1, which will get us 20 over 2, which is equal to 10. So we can make that Facebook collage 10 different ways. All right, let's look at example B. In how many ways can you select a 4-person committee from a set of 10 people? So we're looking at a combination. We have 10 people in the 10 people in the committee. I've just had 10 people and we're trying to choose a 4-person committee. So out of 10, we want to choose 4. So it will be 10 factorial over that 10 minus 4 factorial times your 4 factorial. And I'm only doing this side and then this, just so you understand. It's just like permutations, but you got to add another part. Well, not add it, you're multiplying, but you're putting another part in there. All right, so we have 10 factorial over 4 factorial. 10 minus 4 is 6 factorial. So we'll have 10 times 9 times 8 times 7. We'll stop at 6 factorial, put our 4 times 3 times 2 times 1 times our 6 factorial. Those will cancel. If we multiply 10 times 9 times 8 times 7 up here, we will get 5,040. 4 times 3 times 2 times 1 will get us 24, and that'll get us a total of 210 combinations of ways that we can choose that 4-person committee out of 10 people. All right, so let's go look at counting card hands. In the game of poker, 5 cards are drawn from a standard 52 card deck. How many different poker hands are possible? So 52 cards is always going to be the number of cards in your standard deck. So example 5, and we're looking at part A. So here we're going to choose, out of 52, we're going to choose 5. So that's going to be 52 factorial over 5 factorial times 52 minus 5 factorial. So remember I told you that it gets better with these if we're going to end up with big numbers. We're going to have a big number here. So we'll have 52 factorial times 5 factorial, and 52 minus 5 will get us 47 factorial. So this will get us 52 times 51, counting the wrong way, sorry about that, 51 times 50 times 49 times 48 times 47 factorial divided by 5 times 4 times 3 times 2 times 1 times 47 factorial. The 47 factorials will cancel, and we're going to end up with 3,118,75200. And then on the bottom, 5 times 4 times 3 times 2 times 1 will get us 120. So we will end up with 2,598,960. Big number. So if we look at parentheses, we're ending up with 2,598,960 ways to choose a poker hand. All right, let's go look at part B, big numbers. So as we look at part B, it says, in the game of bridge, a hand consists of 13 cards drawn from a standard 52-card deck. How many different bridge hands are these? So we're choosing, out of 52, we're going to choose 13. So this will be 52 factorial over 13 factorial times 52 minus 13 factorial. So that'll be 52 factorial times 13, or divided by 13 factorial times 39 factorial. So we have 52 times 51 times 50 times 49 times 48 times 47 times 46 times 45 times 44 times 43 times 42 times 41 times 40 times 39 factorial. So it's got a little tiny in the writing. All over 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 times 39 factorial. So cancel those out, and we're going to end up with, let me get the right color here, some scientific notation, because it's going to be some really big numbers. You're going to have to do it in parentheses, divided by a parenthesis. So you would end up with 6.3501 35596 times 10 to the 11th. Well, that means there's 11 decimal places. So we're going to move this over 11 spots. So it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9. So I need to add 2 zeros. So 63501 3559600. So if your calculator gives you that, they're just not able to put all the digits in. So remember, you're moving it to the right. You'll move it 11 places. So that will, we've got 9, so we'll add 2 zeros at the end. I wouldn't give you a problem that big on an exam, because that would be a little bit on the tedious side. All right, let's go look at example 6. So for example 6, the Division of Student Services at your school is selecting 2 men and 2 women to attend a leadership conference in Honolulu, Hawaii. If 10 men and 9 women are qualified for the conference, in how many different ways can management make its decision? All righty. So let's talk about how many there are. So there are a total of 10 men and 9 women, right? So we have 10 men plus we have 9 women, which makes it 19 people. So if we want to choose 2 men and 2 women, we're looking for 4 people. So if we do 19, choose 4, it won't work because we need 2 women and 2 men. If we just choose 4 people, we could end up with 4 women, we could end up with 4 men. So this one does not work. What we're going to have to do is do the 2 women and then do the 2 men, or do the 2 men and then the 2 women. So we're going to start with the women. We're going to do step 1, and we're going to choose the 2 women. So we're looking at choosing, out of 9, choosing 2 women. So that'll be 9 factorial over 2 factorial times 9 minus 2 factorial, which is 9 factorial over 2 factorial 7 factorial, which gets us 9 times 8 times 7 factorial, and 2 times 1 times 7 factorial. Well, the 7 factorials will cancel. 9 times 8 is 72, and 2 times 1 is 2, so that'll get us 36 ways. Now we're going to go to step 2. So step 2 is going to be 2 men. So we're going to, we had 10 men, we're going to choose 2. So that'll be 10 factorial over 2 factorial times 10 minus 2 factorial, which is 10 factorial over 2 factorial times 8 factorial, which is 10 times 9 times 8 factorial over 2 times 1 times 8 factorial. So 10 times 9 is 90. 2 times 1 is 2, which will get you 45 ways. Now, what you're going to do is multiply 36 ways times 45 ways, and you'll get 1,620 ways. So that is your total. You'll have to take this one and multiply it by that one. All right, example 7. We're going to form a governing committee. Assume that you and 15 of your friends have formed a company called Net Media, an internet music and video provider. A committee consisting of a president, a vice president, and a 3-member executive board will govern the company. In how many different ways can this committee be formed? So let's look at it again. You have you and 15 of your friends, so that's a total of 16 people. You formed a company. You want a committee consisting of president, vice president, and then you want a 3-member executive board. So the president and vice president will be specific people. That's going to be a group of 2. But the 3-member executive committee, order won't matter, but the president and vice president order matters. So how many ways can we do this? So example 7. So we know that we talked about we have 16 total people because we have you and 15 of your friends. We want the pres and vice pres. That's 2 specific people. And then we want a 3-member board. And that order doesn't matter. So for step 1, we want to do the president and vice president. And this order matters. So when order matters, that's when we go back to permutations. So we will look at P. Out of 16, we're going to choose 2. That'll get us 16 factorial over 16 minus 2 factorial. So we're doing the permutations, and we're being picky with the permutations, so order matters, and when we're picky, we only have the subtraction happening. So this will get us 16 factorial over 14 factorial, which is 16 times 15 times 14 factorial over 14 factorial. That leaves us a 16 times 15, which will be 240. Now we need to do step 2. So for step 2, we want that 3-member board. And order does not matter. So, how many do we get to choose from, though? Up here we chose out of 16. But now we've taken 16, we've subtracted the vice president and the president. We only have 14 people left to choose from. So we're going to, out of 14, we're going to choose 3 for our committee that we're having. So this will be 14 factorial over 3 factorial times 14 minus 3 factorial, because now we're doing the combo. So that's 14 factorial out of 3 factorial. 14 minus 3 would be 11 factorial. So 14 times 13 times 12 times 11. 3 times 2 times 1 times 11 factorial. And make sure you write the factorial. You can't just write 11. You have to have the factorial part there, or you're changing what it is. So 14 times 13 times 12 would be 2184, divided by 3 times 2 times 1 is 6, which will get you 364. Now, just like on the previous one where we multiplied, our final answer we have to multiply. So we're going to take our 240 ways times our 364 ways, and we'll get 87,360 ways to get a president, a vice president, and 3 different committee members.